In the previous lecture, we saw that if I have a distribution of charge, then the energy of this, or the work done in assembling this charge, is given by 1 over 4 pi epsilon 0 1 half rho r prime over r minus r prime dr prime. We are now going to solve an example for a given charge distribution. For this, we will take a sphere of radius r, which carries a uniform charge distribution rho inside. So, charged sphere with uniform charge density rho over its volume. So, the net charge is going to be 4 pi by 3 r cubed times rho. If I were to calculate the energy, I will do it in two ways, so that you see the equivalence of assembling the charges and this expression that I have written above. Let us first take that I assemble the charges, so that in between, when I have a sphere of radius small r, I bring in the new charge, and that would be I add a small shell over it that also carries density rho and is of thickness dr. How much work have I done in doing so? The work done will be equal to potential at r times the net charge that I have brought in, and that will be 4 pi r square dr is the volume times rho. Now, potential at r due to this black sphere that is of radius small r is going to be equal to 1 over 4 pi epsilon 0 times the charge inside this r radius sphere divided by r times 4 pi r square rho dr. Charge inside the sphere of radius r is 4 pi by 3 r cubed times rho, and therefore, the energy of this distribution is going to be 1 over 4 pi epsilon 0 4 pi by 3 r cubed rho divided by r times 4 pi r square rho dr. Let us work this out. Let me cancel this 4 pi. So, I get 4 pi over 3 epsilon 0, this row here and this row here gives me rho square, this r cancels with r cubed and gives me r. So, I am left with integration of 0 to capital R, because that is up to which the charge has been assembled, r raised to 4 dr, which gives me an answer 4 pi by 3 epsilon 0 rho square times r raised to 5 by 5. That is the answer. Let us write this in terms of the charges. We have already seen, let me write it on the side, that q, the net charge, is 4 pi by 3 rho r cubed, and therefore, rho is equal to 3 q over 4 pi r cubed. Substitute this here and you are going to get is equal to 4 pi by 3 epsilon 0 rho square, which is 9 q square divided by 16 pi square r raised to 6 times r raised to 5 over 5. This 4 pi cancels with this, gives you 4 pi. This 3 cancels with this, gives you 3. So, So, you get the energy equal to 3 over 5 q square divided by 4 pi epsilon 0 r. That is the energy of a uniformly charged sphere with density rho. Let us calculate it using the other expression that we had derived, where we had said that energy is also given as 1 over 4 pi epsilon 0 1 half integration rho r prime over r minus r prime dv prime. One point, I keep sometime writing dr for dv and dr prime for dv prime. So, do not get confused. Now, I can write this as 1 over 4 pi epsilon 0 1 half integration dv rho r, and this term rho r prime r minus r prime dr prime dv prime combined with 1 over 4 pi epsilon 0 is nothing but, I will remove this also, nothing but v at r. But notice that this v of r is due to final charge distribution. Just before this, when we solved for the energy, we first calculated v at r due to charge inside. Now, this v of r is the potential due to the final charge distribution, because what I am taking here, this rho, is the total charge density or charge density due to the full charge distribution. Now, in one of the assignments earlier, you have solved for this v of r, and this v of r is nothing but, if you recall, 1 over 4 pi epsilon 0 3 q over 2 r minus 1 half q r square over r cubed. This is one of the assignments I had given earlier, so that you can see that this is equal to 1 over 4 pi epsilon 0 q over r for r equals r. Therefore, the total energy is going to be given as 1 half integration rho r, which is a constant dV, and let me write the potential 1 over 4 pi epsilon 0 3 q over 2 r minus 1 half q r square over r cubed. The first term is a constant. So, this comes out to be equal to, the integration comes out to be equal to this charge q times this constant, and therefore, I can write this as 1 half q times 3 q over 2 r, and there is a 4 pi epsilon 0 in the denominator, minus the next term is going to be this 1 half, and this 1 half is 1/4 q over r cubed. There is a 1 over 4 pi epsilon 0, and I am left with integration rho, which is a constant, times volume integral is going to be 4 pi r square dr, and I already have an r square from here. Let us see if we have taken care of all the terms. 1 half and 1 half gives me 1/4. This we have taken care of. Q over r cubed, 1 over 4 pi epsilon 0, which is taken care of here, and then rho times 4 pi r square dr. This is fine. So, I can now write this as equal to q over 4 pi epsilon 0 r, q square over 4 pi epsilon 0 r, and I am left with 3/4 minus q over 4 pi epsilon 0 r cubed 1/4 times rho times 4 pi. These are the constants coming from here, and then I have r raised to 5 over 5, because this integral is from 0 to r. So, this comes out to be q square over 4 pi epsilon 0 r. Let us take this out. I am left with 3/4 minus q 4 pi epsilon 0 r we have taken out. So, 1 over r square times 1/4 times 4 pi r raised to 5 over 5 times rho over q. Let's again now cancel a few things. This r square with r 5 gives me r cubed here. So, I am getting equal to q square over 4 pi epsilon 0 r 3/4 minus 1/4 times 1/5 4 pi r cubed rho over q. 4 pi r cubed rho is 3q, and therefore, the energy I get is q square over 4 pi epsilon 0 3/4 minus 1 over 20 times 3 over q over q. This q cancels, and you get, there is an r here, q square over 4 pi epsilon 0 3/4 minus 3 over 20, that is q square over 4 pi epsilon 0 times, this will be 12 over 20, which is nothing but 3/5, which is 3/5 q square over 4 pi epsilon 0 r. Same answer as earlier. So, we have now solved for a distribution of charge, the energy of a distribution of a charge with two different methods. One, we thought of this being assembled by bringing charge from outside, and therefore, we did calculated the potential due to the existing charge and multiplied by the brought in charge, integrated, and the other, the direct expression, which is 1/2 V r rho r. So, finally, to conclude this, we have seen that if there is a charge distribution or a collection of charges, I can write the energy of this system as 1/2 times 1 over 4 pi epsilon 0 integration rho r prime over r minus r prime dv prime, which is also equivalent to 1/2 integration V of r is the potential due to the full charge distribution times rho of r times dV. In the case of charge distribution consisting of point charges, rho goes to nothing but the delta function, and I will get back my expression I j I not equal to j q I q j over r minus r I minus r j summed over 1/2 and 1 over 4 pi epsilon 0. In making this transition from the continuous distribution of charges to charge distribution consisting of point charges, you have to be careful that in this case integration rho r dV for dV tending to 0 does not go to 0, because these point charges are like delta functions, and therefore, in doing the integration I have to explicitly avoid the self interaction of charges. Remember earlier when I was discussing this formula, I had said that in a continuous distribution, this rho r dv integrated over a smaller and smaller volume, macroscopically very small volume goes to 0, but in point charges it does not. So one has to be careful. I would like you to make this connection after hearing this lecture.